इधम आ जाओ यहाँ and now you come in, you can.
Hello, good morning, everyone, and good night to Tim, but not yet to hit the bed. So, hello, everyone. Sorry for this delay. Tim, you can see that on the chat window, there somebody is requesting to ask questions. So, related to last week's session, Vandana. Will
Okay.
she ask it now or?
Yes, go ahead.
Yeah, sure. So, we'll tell her. So, Vandana, you can ask your question.
Yeah. Hello, everyone. I just wanted to know how valid is it if we take the statistics for the data that is maybe the mean, the standard deviation for the data related to the star before the transit, and we consider the same standard deviation for the data during the transit.
Okay. That's a pardon me. That's actually a good question. There should not be a very large change in the standard deviation under ideal conditions, and the reason is that we've got the largest drop in the brightness during a transit that I'm familiar with is maybe 1%. In these cases of the hot Jupiters, and so you're not going to have the signal level drop enough to get a very large change in the standard deviation. If you do have, let me think though, if there is a larger standard deviation, it could be because something else is going on. The fact that you're getting maybe a different change from one transit to another that could lead to what appear to be larger standard deviations, but because you're overlaying multiple transits. But in general, at least in the idealized case, I think that you're just not going to get a large change, or that you could account for any changes in it purely as a matter of by what fraction does the signal drop. I'm sorry, does that answer the question well? I might have misunderstood.
Yes. So effectively, then it would depend on the instrument. If we are, I'm sorry.
Sorry, go ahead.
Yes. So if we are assuming that the star, when it's not in transit, there are no variations in its brightness. Yes. So effectively.
I can't hear the audio.
Hello.
Yes, that was very faint to me too, just a moment ago.
Yes.
Yes, I think I've got the answer to my question, so I think it's fine.
Okay, good. I'm
But
glad.
Tim, I had a question.
Yes.
Why should one assume that there should be a change in stellar parameters in a transit, right? I mean, in principle, it's just
I'm sorry, could you repeat? There was a little bit of static in the middle of one of the words.
yeah, yeah. No. So I was asking why do you think is it wrong to assume that there's no change in the stellar parameters during the transit, right? Because the transit is just a geometrical situation, right? There's no
Yes,
need for us to assume that there's going to be a change in stellar parameters in a transit.
correct. Right. And so your standard deviation could increase. The only thing that I can think of is that it would increase maybe because your the total light you get from the star is fainter, but by a small amount. And if one transit is a little different from another transit by some reason, then by adding several transits on top of each other, it may increase the standard deviation there. But in that case, then you could actually make a more sophisticated model that accounts for it. In fact, this is a technique that's being used to look for additional planets around that star. If another planet that has not caused a transit directly, but it may gravitationally pull on the planet that is causing a transit. And there's what's called transit timing variations, TTV. And if you have a transit that occurs a little bit early or a little bit late, maybe just by very few minutes, this could be due to the presence of an unseen second planet, uh, causing the orbit of the first planet to precess.
Mhm. Yeah.
Thank you.
So thanks, Tim. Shall we start on today's job?
Yes.
Yes. And sorry to interrupt, but students, you all can continue putting your questions on the chat window, and
Okay.
Tim can take it whenever he wants. Right?
All right.
Okay.
Okay.
Yeah.
Well, folks, I'm sorry that we're a little bit late tonight. This is because this morning, this is because I actually had my internet go out just as I was getting started, and I couldn't get the connection to Priya there. I had to switch over internet providers, but I'm glad that Priya, that you were able to get me on the phone there. Uh, and thankfully, we have a backup internet here. So tonight, this morning, we're going to be taking a look at the first of two sessions on globular clusters, taking a look at the ages and the distances of globular clusters in the Milky Way galaxy. What I'm going to do today is to look at the photometry, how to measure the brightnesses and colors of stars in a cluster. And there are different ways of doing this. I'll cover one that's, let's say, the easiest introduction to it, and where to get the data as well. And then next week, I'll go, after you've already got data for a few clusters, and we can go through and take a look at making what's called a color magnitude diagram, which is a diagnostic diagram that tells you about the age and distance of the cluster, among some other things too. Okay, so let's see. Let me make sure that everybody can see my screen here. It should say chapter 17 on that. Let's see.
Yeah.
And
Pause.
I'm going to post that in the chat window. This is like last week, a chapter excerpt from the observational astronomy book that I've got here. So let me put in the file onto the chat window. Okay. And that's 2 megabytes. It's about halfway finished loading right now. So the first thing to do is, well, we want to be able to get the data. So, all right, the file is loaded up in the chat window. So we want to be able to get the data first. So first you need to know what it is you're looking for. There are many lists of globular clusters, and I'll pull up some of these right here. Let's see. Now I went through and made a list of those that have been observed with the Hubble Space Telescope, for example. I've just gone through that there, and I've just put yeses and nos on several of these that I had found in the archives. Uh, the ones that we're going to be working with first are from the Sloan Digital Sky Survey, and I've made a list of several of these here that have worked out fairly well in the Sloan. And you take a look on page 89. That is the third page in the PDF file under data sources and software. So you see here we've got some large Messier clusters, and then NGC. Um, Depending on what your background on these are, the Messier catalog with M1 through M110 catalog was made by Charles Messier in the late 1700s. So those are relatively bright nearby objects which can be seen easily with even a backyard telescope and sometimes binoculars or the naked eye. The NGC refers to the New General Catalog, which was created a little over 100 years ago. And this goes out much farther and is using larger telescopes. So these tend to be a lot fainter, but all of the Messier catalog, all of the galaxies, clusters, and things in the Messier catalog also have an NGC number. And then I've also included one from the Mount Palomar. That's a large, well, it's now a fairly old observatory, but the Mount Palomar Observatory in the United States, I believe California, and they did a survey of globular clusters in the Milky Way. And so that's Palomar 5, for example. Okay, so if you have a list of the globular clusters and you find some that are within a the catalog of an observatory, then you go and you download that there. So let's try out one of these here. If you follow along, we're going to follow the instructions on, again, on page 89, and we're going to go to the Sloan Digital Sky Survey. So if you get up your web browser, you go to sdss.org. Now, one thing about the Sloan is that they change their website maybe a little bit too frequently. And so I had to go through and make sure that the information in the book here had not gone out of date. You'll go to data. Also, maybe I should go back just a little bit here first. So if you're not familiar with it already, the Sloan Digital Skies Survey was really the first large-scale survey of the skies done with an all-digital imaging from the beginning. It is, in a sense, a follow-on to the earlier digitized sky survey, or DSS, which you'll see in many observatories as just a sky chart that you can use to see what a general view of the sky looks like in any direction. The digitized sky survey was simply scanned in to computers, well, sophisticated scanners, mind you, from photographic plates made starting in the 1940s. Um, National Geographic magazine had helped with some of these, and there were a few other sources there. And so these continued on several surveys using different color filters and different film on up into the 1980s and I believe the early 1990s. By that point, they saw the value of scanning them in and having them made digital. Um, but so these large surveys were done using glass plate negatives on up until just a few decades ago. Glass, uh, a photographic emulsion on glass has a value in that it does not expand or contract very much with heat, and so it maintains the same scale. When they had started off doing these back in the 1940s, even though we had some of these digital cameras by the 1980s, the cameras were very small at that time, and the image quality was not as good as what you could get from a glass plate. And so they continued on there. You didn't want to change technologies in the middle of a survey. So the Sloan came along in the 1990s, and they started from the beginning with a large digital camera, and they observed in 5 filters. In fact, they used what was pretty much a brand new filter set, U, G, R, I, and Z filters. U is ultraviolet, G is green, R is red, I is a near infrared filter, and Z is a slightly longer near infrared filter. And all of these we use the lowercase letters for. Okay, so that's a little bit of the background. Let's click on the data link there. And again, all of these steps are listed on page 89 of the file. All right, data release 16. So every time they go through, they collect another set of data, they process it, it takes them a while, they calibrate it, and then they release the data as a catalog and as images. And so that's data release 1 was the very first they did, and now they're on data release 16. Each one of these comes out. It's more than a year in between them, in between them. Okay. So data release 16 here is the current one. We'll select at the top here, we see data sets, imaging data, optical spectra, because they do follow up with chemical spectra for several targets. And then some of their other projects here, Apogee, Maystar, Manga. This is an integral field unit, which is a combination camera and spectrograph, and then help and tutorials. So we'll go to imaging data. All right. Now, here we have different ways we can get to the data. Sky Server is actually a very user-friendly interface. I'm going to bring it up in a separate window, a separate tab here. This is just to show you what it looks like. This is an older interface they've got. I guess they've updated it for the new data release. But if you look under Data Access and you click on Navigate, you get what is a kind of their version of an old mapping software. If any of you remember the early days of computer maps with MapQuest, this is kind of the setup that MapQuest had there, with bars for going north, south, east, and west, like that there. And so you see the sky there. You can zoom out with the magnifying glass, or zoom in. And whichever target you're on here, you can switch targets like that. And you can take a look at the spectrum, things like this. They've already processed it and identified various lines. Okay, but that's a nice place where you can look around, and it's sometimes useful to put in the coordinates, right ascension and declination, and hit search, and you can see whether the target you're interested in is within the field of view of this survey. Not all of them will be, because it's only looking at a slice of the sky and not the entire sky. Okay. So CAS jobs is one that you can use with the SQL query language. It's a database language, also called SQL. That is a very handy technique for getting a whole lot of files. But we're going to go through the Science Archive server here. So we click on the bottom, Explore SAS Imaging, Science Archive server. So click on that now. Slowly. All right. So here we can get imaging, optical spectroscopy, and infrared spectroscopy. SDSS3, this is their third phase of their project there. We're going to do a single field search, field meaning field of view. So what did the camera see at one time? If you wanted to get several of them, you'd go to the bulk field search, and then there are other ways of displaying it. So click on single field search. Now, if you have not followed along, if you got behind, your computer might be behind here, I'm going to post in the chat window the link to go to this directly. All right. So now we can put in the object name. We can put in right ascension or declination, and we can put these other things here. Now, just so you know, because you'll see it pop up a little bit, the Sloan has a unique way of referencing these fields with what's called run, cam call, and field. Run is, well, every time that they run the equipment, that's a run. I don't know exactly how much more precise that is. Camera column, they have different columns in it. That's not a pixel column. It's a camera column because of how it's put together, and then a field within that there. And each of the images that comes down will have run, cam call, and field listed. But we don't know about that yet. All we want is the object name. Okay, so we're going to start off. If you take a look at the list on page 89 here, let's go to this promising target here, number 9 on the list. NGC 5466. And I'll put that in the chat window to make sure that everybody can see that clearly. Okay, and if you put that in the search for object name and submit, scroll down, and there we have it. You should see a color image of the cluster. Okay, hold on, I'm making sure that I've got that all there. All right. Now below it, you can download at each of these links a JPEG of the whole color field, and then fits images. Trying to remember with what we did last time, we didn't cover the image file formats, and fits is the flexible. Let me see here. Flexible
Image transport system.
image transports. Thank you. All right, flexible image transport system. And so this is a lossless file system, a file type, which it does not do. You can compress it, but you don't lose any information when you compress it. And so each pixel is represented with a full dynamic range there, and it has header information. So we have 5 separate images. Each one is black and white with a different filter in place: U, G, R, I, and Z. Here we have these filters again, listed like that. And here they list the header information for that's common to all of them. We're going to use 2 for this. We're going to use the G or green and the R or red. So you just click on it. In some browsers, you might have to do a right click so that it doesn't come up in the browser window. Okay. And so you'll see that it's going to, let's see, make yourself a working folder here. I've already got this downloaded, but I'll show you. And it'll have .fits and then .bz2. And that's a file compression format there. Okay, so download G and then do the same for R. And I'm going to bring up my window. All right. So we have these 2 files here. Now on a Macintosh computer and maybe on Linux systems, Unix and Linux systems, you should be able to automatically decompress this with the archive utility, and it should come up as a fits. On Windows, I don't know which tool decodes that, but let me see here. WinZip, WINZIP, is one that you can use. All right. But I'll hope that you're able to get these decompressed very quickly there. Okay, these come up as a little more than 12 megabytes each. I'll warn you, when you download, I'll show you how to do it from the Hubble at the end of all of this. And those can be very large files, over 100 megabytes each, and you get several at a time. So you can wind up downloading a gigabyte just for one target very easily. Make sure you've got space. I've got an external disk drive that I use for those. Okay, so we have those 2. I'm going to discard the compressed file so I don't run out of space on the computer. This little laptop here is just about out of disk space, unfortunately. I'm going to have to use more of these external disk drives. Okay. Now, for displaying the image, tool I recommend is DS9, and I believe we talked about this last week. So DS9 is an image display tool. Actually, wait a second. I'm sorry. I'm thinking of my class with DS9. I was going over some similar stuff with them. So this program here, let's see, SAO image DS9. You can get this from, let's see here, SAO DS9. Now, if you just Google DS9, what you're going to come up with is fan web pages for Star Trek, because they named this tool after the Star Trek series. Here we go. I'm going to copy this into the chat window. Ah, it has been discussed. Okay, thank you. Okay, and this runs on multiple platforms there. By the way, they named it, the Star Trek series they named it after was called Deep Space Nine. And there has been a custom of the Smithsonian Astrophysical Observatory naming their image programs after Star Trek series. The previous one they had was called SAO Image TNG, which stood for the Next Generation, named for Star Trek: The Next Generation, and they even had the Star Trek symbol on it. They really weren't, they were not being subtle. Okay, so let's say that you've got DS9 up now. So we're going to open up the image. All right, now I have this here. Let's get G. Let's open up the G file. All right, if you have that open there, and it's good to, if you haven't played around with it very much, it's good to just play with this some. The things that you really need to be able to do quickly with it are to zoom in and out. On the Macintosh, at least, I have it set where I can do a 2-finger scroll up and down, gets me in and out. You can go into the preferences, and there are lots of preferences you can do there. Get it just where you like it. And you can do with the certain, you might have to hold down a key to click on that, but you can adjust the contrast, brighter and brighter and dimmer, and then low contrast to high contrast like that. Okay. All right, so there we have an image, and we can see the cluster very clearly. Let's set the scale. We'll go to logarithmic scale because our eyes respond to light logarithmically, and we get a better view of the dynamic range. And you can go to from minimum and maximum, or you can get sophisticated and go to parameters and pull up a histogram here and see what your high and low values that you want to have are. All right, so I'm going to do it about like that there. Okay, so now we've confirmed that we've got a good view of the target, and I'll hit the frame selection and tile and pull in a new image. And here I'm going to put the red frame. Okay. And they seem to be pointing the same way. Now, one thing to notice here, and this is important when we get on to making our star catalog, is that these two frames are not precisely lined up. If I hit blink, you see as it blinks these back and forth, it goes from the first field to the second, there's a very slight shift here of a few pixels. And that's going to throw off the technique that we're using, but we've got ways of overcoming that there. It'll just take a few more steps. Okay, I'll hit tile and stop the blinking. All right, so now that we have that up there, I'm going to quit SAO image because we have confirmed that we got what we wanted. And the next thing to do is to get this, what's called the Aperture Photometry tool, APT. Now, there are several different kinds of software you can use to do the photometry. This is one that I think gives a nice, easy overview, but you may have also been introduced to QPhoto or QuickPhoto with IRAF, or the Photo software, which does a more sophisticated approach. I'm going to give you a link to APT. Let's see here. I'll pull it up on the web page here. Aperture Photometry tool. Okay, and I'm putting that in the chat window as well. All right, to go to this, you just go to the download link. And zip file for Windows, tar.gz for Linux, and a DMG, that's a disk image, for Mac. So you can just click on one of these here, Windows, Linux, or Mac. And it's not a particularly difficult one to get running. On the Mac, you might have to, it might say the file is broken or whatever, which is just because it doesn't recognize the developer. So you would go through, if you have any problems, go to the frequently asked questions, FAQ, and if you're on a Mac, why does my Mac tell me the DMG file is damaged? And it has some installation instructions for you there. All right. So once you have that there, open up the Aperture Photometry tool. So the Aperture Photometry tool it includes a fits image viewer in it, built into it. So we can open the image. Now, one thing is its file browsing is not particularly sophisticated. It never remembers the last place you've been, unlike a lot of the others on the system. So we'll have to scroll through every single time. Now, I put this all under research. Where's R for research? And then workshops. Okay. Globular Clusters Photometry. Okay, and here I have my files. So again, we're going to start with the G file here, the green image. We could start with either one. Probably the red one might be a little bit more sensitive, and it could make some sense to start with that, but I haven't seen large differences. Okay, we see a segment of the image come up in the right-hand side here. And I'm going to make the window a little bit smaller because I have a small laptop to fit it on the screen there. All right, in the middle, we have a magnifier window. In the lower middle here, we can display it 2, 10, or 20 times. Okay, there we go. And here we have a whole lot of somewhat intimidating looking controls. But to tell you the truth, I do like the graphical design of this software. It is fairly easy when you know the steps to get it up and running, and you can see where all the options are. If you're using one of these that's all from the command line, you can sometimes it's easy to forget what's what. So we've opened the image. The first thing we're going to do is, well, look at my instructions here. All right. So back to the instructions here, and let's go to page 92 on this, which is the seventh, let's see, seventh page out of the PDF file. So section 17.2.2. Now, the idea is, with aperture photometry, there are at least two different ways of measuring the brightness of a star. The one that we're going to use is called aperture photometry, and the idea is that we will draw a circle around each star. That'll be the aperture, the opening. We're going to add up all the light within the pixels inside that circle, and we'll say, all right, this is the light from the star, but we've also got background light from the sky, and we need to remove that. So we're going to draw an annulus, a ring around the background, a ring around the star farther out, and we'll average out the brightness of all the pixels in that ring, that annulus, and we'll say, okay, this is the brightness of the sky itself per pixel, and we will subtract that value from every pixel inside the aperture, inside the circle that we've got around the star. And we'll say the difference between those two, that's the light coming from the star itself. And so we do that for all the stars in the picture, and we have our catalog there. This works fairly well when you do not have a crowded field, if you don't have too many stars in there. And even with a globular cluster here, this actually works pretty well. Okay, there's another way of doing it though, And that is when you get a very crowded field, and in the middle of this here, that might be a somewhat crowded field. You see how the images of the stars are overlapping. In that case, you can do PSF matching. PSF, that stands for point spread function, and that's the diffraction pattern of the light coming through the telescope. So the PSF, the diffraction pattern, is distinctive for that telescope, and there's a way in which the light is spread out, which will be the same for every star. If you know the shape of the point spread function for the telescope, then you can use that as a model and you can fit it to each place where there's a star, and you scale it brighter and fainter and you can center it properly. And then if several stars are overlapping, then you can still get the contribution of the light of each of those stars separately fairly well. And there's a good reason that we could use that here in this. So some of the tools with the IRAF package are PHOT, P-H-O-T, and that does photometry, and I believe it does use the PSF fitting method there. But I have not used that, but only once, and so I don't have enough experience to give you a good overview of it. So we'll try with this one here. Now, the first things we do with the APT file, once you got it up, is we're going to, let's see here, we go to more settings. So watch my cursor. If you go down to the very bottom, you have these buttons near the bottom. More settings is on the bottom left. Click on that. All right. So source algorithm, we're just going to leave it at model 0. That means this is telling it whether it should fill in estimated values for bad pixels, or maybe for all the pixels even. And we're going to leave it as no interpolation there. Sky algorithm, A, B, C, D, E, and F, whether we use an annulus, that's the ring around the star, or if we have a more crowded field, we can use a different technique. This is model F. So you're either going to use B if it's not too crowded, or F if it is crowded. Now, the F method is because if we've got a whole lot of stars, oh, and look, they do have an explanation that pops up when you put the mouse over it. If we've got a lot of stars and they're starting to get crowded in together, then in the region where we're trying to measure the sky, there are probably going to be several stars in there. And in method B, it will take the, let's see, I think it's the median, median. It'll take the median value of the pixel in the annulus surrounding the star, and it'll say, all right, that's going to be the value of the sky. But if there are too many stars in that annulus, then it can't get a good measure of the sky value. And instead you use model F, where it takes the entire field of view and it does statistics on it, and it looks for little sections of faint pixels that are between the stars, and it makes a map and it says, all right, this is the background value. So in this case here, I think we'll use model F. Okay, B or F, either one. We'll use F in this case. All right, the only other thing you need to change on this here, we can ignore most of this. We have to go down to the 0 point. I imagine you may be familiar with 0 points now, but that is the value of the magnitude where it's a reference magnitude. So it would tell you how much flux there is for a magnitude of 0, and we can turn that around. It sets the 0 value for the magnitude scale. I'm getting my words mixed up. Now, for any of the Sloan Digital Sky Survey images, that value is 22.5. And for anything else, you'll have to look it up. Sometimes it'll be held in the header of the image file, and other times you have to look it up on the website for the observatory. Let's take a look at what these other things are. Custom sky value, we don't need that. Use centroid in photometry calculation. That means that when it identifies something as a star, it's going to take that aperture, that circle, and it's going to center it using a weighted average of the brightness of the pixels. And so it will try to get it where the weighted average of the center of the star is where it centers the aperture. And it will snap the aperture to the centroid. Okay. Um, Reject source values less than or greater than these. This is where you have just bad data there with extremely, look at that, 10 to the 308th power. Well, I guess if it's reading something like that, something is definitely wrong. Bunnet. All right, this one always sounds a little funny. Bunnet means brightness unit. And that is in the header file for the image. And it tells you what kinds of units are being used for the flux. This is the rather adorable name of a nano Maggie. Maggie is also an English girl's name, so that's why it sounds kind of cute to me every time. Nano Maggie is a, actually I had to look up the exact definition, but that's why Wolfram Alpha is such a useful web page. And I'll show this to you here. Okay, so a nano Maggie is in terms of Jansky's. It is, oh, hang on. I looked up Jansky. Let's see, nano Maggies in Jansky's. Okay, here we go. All right, so the nano Maggie is, they take the flux, so nano Maggie is 1/1000th of a Maggie, and they use the logarithm of the flux, so this is going from normal magnitude, and they simply have that 22.5 as the 0 point here. So they just take that as a number like that. And because the brightnesses are so faint, they put that as their brightness unit. Okay. Let's see here, depth of coverage, gain. These are technical pieces of information about the camera. We don't need to worry about that because we have the brightness units are already calibrated in there. All right. So select model F. In other cases, you could wind up using model B, but I recommend only one of those two. Put in 22.5 for the 0 point. And what you do next is you apply settings. Okay. Now, because we chose model F, it's going to have to scan the entire image and make a map of the values it thinks are the sky there. Do you want to do that now? And yes, you do. Okay. I think the default values are probably good, so we hit compute, and it should be done very quickly. All right, I close the window, and I can close this window as well. By the way, if you had chosen model B, it would not do that. All right, the next thing we do is, get my instructions here. We're going to go to, see where it says here, click on the big button on the right to change aperture attributes. So click on the big button on the right. Okay, and now we get a picture of the annulus. So the red circle in the middle is the annulus. Let's say that these crosshairs are centered on a star, which they are not right now. In fact, I think I could, I'll click on one. There we go. All right, I've snapped it into place. Now I go back and click on this. So now you can see what that's going to look like. You don't need to do that yourself. All right, it tells me where that aperture is, the coordinates X and Y. We're going to keep this box checked and make it a circular aperture. You have the ability to make an elliptical aperture. So if you were looking at a galaxy, say, you could do that. We're going to be dealing with stars, which certainly ought to be round. Now, the next thing is I recommend that you increase the major radius to be 10 pixels. Now, if you had an ellipse, you'd have a major and a minor radius. But because we've got a circle, we've only got one, which is the major radius. So put that as 10, hit apply, and now we see it bigger. Okay, so the red circle is the aperture, and the annulus where it would measure the sky, if we'd chosen that other sky model, that annulus is between the green and yellow circles here. Right? So you see what they do is, for aperture photometry, you draw the circle around the star here, but then you leave a bit of a gap because the star, the brightness of the star, the point spread function does not cut off at any radius. In principle, it extends out to infinity. So if you want to add in, you want to include where the signal to noise in that diffraction pattern is high enough to get good data, but you don't want to measure the sky right outside that because you could still be getting a bit of contribution from the star itself. So that's why you give a bit of a gap. All right, we hit apply and then we hit close. And now here you can adjust, if you were using that method B for the sky, you could adjust the inner and outer radii of the annulus and hit apply and then close, but we're not doing that. Okay. So our next step then, I should just leave this over here, is we're going to recompute the photometry. Actually, I'm going to use it in my second window. Now, if you go down to the lower left corner again, there's in red, it says recompute photometry. Now, this is just a color scale here. We don't need that. Once you hit that, you should see numbers pop up in this bottom region here. Share the chapter in the chat. That's already posted there. Let me put it again. If you come in a little bit later, I don't know if you can see all of the chat. So let me do that again. Just a moment. Okay. And it is, oh, I see, you got disconnected. Okay, that should be up again now. You should be able to see that. Okay. All right. So now we have hit recompute photometry, and so our photometry, some little tests wherever we've clicked in the window here, we see some numbers that show up: sky background, sky scale, sigma intensity, uncertainty, and then converted to magnitudes. All right. Now let's go to the next page. This is page 94 in the chapter. All right. To get started, let's make sure that there is not already a list of stars in memory. Now, if you just open this up, of course there isn't, but you should get in the habit of checking this. So down at the bottom left, you click on List Results, and it says there's no file. That's good. That's exactly what we wanted. If you had already gone through and done one and it was still in memory, then if you create a list of stars now, it will simply append that to the end of that list and it will make a mess of things and we'd have to erase it. Okay, that's fine. Now, let's go over here to the bottom middle, very bottom row here, and you see Source List. Click on that. Source List. If we already had a list of stars, then we would be able to choose it, but we don't have one yet. So we need to create the list. This is where it goes through and it uses the statistics on what it thinks the background level is and how many standard deviations brighter than that it should use as a threshold to say, this is a star or a galaxy or something. Okay, so we'll create a source list. Now, it says select the type in pixel coordinates or in equatorial coordinates. Equatorial means it must have a world coordinate system, or WCS, attached to it. and that is uh, a method. You put some numbers in the header, which will allow an image display or the aperture photometry tool to know what the right ascension and declination are for any pixel on the picture. But we're not going to do that. We will need that later on, but we're not going to do that right now. We're just going to use the pixel method here. So hit create source list. Okay. Now again, it's the window buttons are a little bit clunky on this. It is going to create this file called source list by apt.dat. That's usually not the name I want to give it, and it's usually not in the location I want to give it either. So we hit reset source list file name. Okay, reset. And that's just to name it and to give it a location. So I'm going to go back to, oh, where was that? Research. Okay, workshops. Here we are, globular clusters. All right, now if you take a look at the photometry chapter, and Priya has said that she's also shared that on Telegram, the chapter on globulars. Okay, we're right here, halfway down the page. So I recommend that you give it a name that is useful. The first part should be the name of the target, NGC 5466. The next one is the filter that's used, and that's important because we're going to be using two different filters, so we have to know which is which. That's the G band. Next, put sources, because this is a list of sources. It's not the photometry, not the brightness of them. And finally, we need to know what um, coordinate system we used. In this case, we're using pixel coordinates. So I'm putting X, Y, or you could put something else that lets you know that. And then dot text. Okay. So I've already got that here, but I'm going to create a new one. Okay, that's that. Choose. All right. And maybe I should, because I'm going to run this, I should probably delete the one I've already got. Or maybe I'll put old. Okay. So now we've got that. Here you have the threshold. So how many sigma above the background it should be before it calls it a star. How many pixels minimum there should be in the source to consider it. Because maybe you have, there are what are called hot pixels, which are artificially on because of damage to the detector. And there are also cosmic rays that'll hit your camera. It turns out that a digital camera is an excellent cosmic ray detector, unfortunately. And if you're using one that is a space-based telescope, like the Hubble Space Telescope, it has a lot of low energy cosmic rays, protons, that are messing around, and they leave these streaks. But those tend to be very sharp spots. So if you have only a few pixels, it could just be a cosmic ray. Maximum number, 10,000. Yeah, you're not going to have stars bigger than that. And these other parts here, I usually don't adjust. Leave these in the default values. If you were to have a problem, then you can come back and change these. Okay, the next thing, create, oh, sorry, one other point. Check box to disable source deblending. Remember, it's going to try to separate one source from another when they overlap, and it's got a sophisticated-ish algorithm to do that. We're going to let it do that. Okay, we create the source list now, and it shouldn't take but a few seconds. All right, processing completed. Now I close the window. Now, again, these were physicists and astronomers who were programming this, probably not professional programmers. So the buttons here, at least in my version, are sometimes a little too wide for the page. You can expand the window so you can see everything. Make sure you can see it all. Okay, the next step is we go to this is the bottom of page 94. Let's see here. Let's get it onto that. there. Okay, the next step is let's see, create source list, reset source name. Okay, if you already had a list, you would choose source list. Now we're going to hit create. Let's see, we've done that. Hang on. All right, caught up with where we are. So now it tells me that it's found 2,388 targets, stars. So that's good. Next, we're going to process the list. Manually, you would just click on it once for each star, but there are 2,000 of them, so I don't want to do that. We can do it automatically. Click on that. Now, if you have multiple processors in your computer, then you should be able, it should be able to thread them through the several different processors. And in the preferences for the program, you can tell it how many you've got if it doesn't find them. Now on my, this is a 5-year-old laptop with, I believe, 4 processors. It takes it about 1 minute to process the whole thing. And you can see the progress down here on the bottom. If it is doing only one thread, one process at a time, it would tell you which target it's on. But here we've got 1,000 something threads that are processing simultaneously, so it doesn't show me that. Okay, almost finished. I'll pull up the instructions here. Okay. And I will note, as it says in the text here, if we had seen number of sources was 0, that meant that we had the thresholds or the statistics set in a way that it simply could not find the list, the sources. And so you would redo the source list by changing those thresholds. Okay, it has processed all of them. So we can close the window. Pull up the instructions again. All right, automatically process list, close window. Now we're going to list the results. You'll find that down at the very bottom again. Save results, list results, and plot results. So I'm going to list the results. Okay. Now, first thing we should do is to check that there are indeed 2,388 targets on the list. The number of each target is on the first column there. If I scroll down to the very bottom, indeed I get the correct number. If you already had a list of targets in memory, it would have appended it to the bottom and you'd have a different number. In that case, you should clear the contents and start over. Now, let's see what information we have. The right ascension and declination of the aperture center, the right ascension declination of the centroid, which is, well, the aperture should be centered on the centroid, but you see that there's a little bit of rounding difference there. That's not a problem for us. The X and Y coordinates in pixels, those are integers. X and Y of the centroid, which is a fraction of an integer, fraction of a pixel. Flags, that's good. 1 is good. If it wasn't able to do the, to model it correctly, you'd get a different number. Here's the key thing though, source intensity. This is in magnitudes. Okay. I believe it's in magnitudes. Okay, 14, 4, 9, so on like that there. 222, that's probably a bad, oh, I'm sorry, nanomaggies. So, and then magnitudes are over here on the right. So we have intensity and uncertainty in nanomaggies, and then in magnitudes, the magnitude and the uncertainty there. That looks more realistic here. Okay, 19th and 20th magnitudes for a lot of these. Okay, and then it has sky values, the mode, average, and then information about the aperture, which is the same for all of them. Radial profile, and then which image it came from. Okay, so now what we're going to do is export the contents of this list to a file. Once again, you need to name it by renaming it. Otherwise, it comes up in the same directory as Excel file.csv. Now, CSV stands for comma separated values. And this is a way of putting in a database or a list of data with comma separating each column. So reset. Okay. And so here, we're going to name it as the target name, NGC 5466, followed by the filter, which is G, followed by phot, or that's just for photometry, because here we've actually got the magnitudes, that's the photometry, and finally .csv, and you do need it to be .csv. Okay, and then you hit choose, and I would not include any of these other options here. Okay, so you go to create CSV file, and then you close the window. Actually, you might find that it is, when you create it, it closes automatically. I've already got the file, so I'm not going to create a new one. Okay, the final thing to do is to, well, actually, before we clear this window here, let's make sure the file exists. So I'm going to pull up my window here. Okay. I'll put up a little preview of it. And there we go. That's it. Okay, so it exists. We've got it saved. Now we clear the contents. Clear the file? Yes. All right. Now we cleared it because we are going to continue with another file. So where we are is on page 96 here. And that's the end of this for the G filter. Now we're going to scroll back to the beginning of this. Page 92, making source lists and calculating photometry. And we're going to do it the red filter image. Okay, so give you a second there. So now let's open the image. Okay, it gives you an option. Do you want to read in a new image and clear all of the comparison images, comparator images? Yes. So we're going to choose option A. All right, which one do we want to read? Thankfully, in this case, it did remember where we had been before. So that's frame R. Notice that the filter name is in the file name for these that come from the Sloan, which is very helpful. That's not true for things like the Hubble. I can close the color table. I take a look in the main window here, and indeed I do have yep, there's the cluster. All right, I just clicked on a star there just so I get an aperture that's visible to me. I don't need to. Okay. Now, let's see. Our first item was to go to more settings, but just to make sure that the options were where we had wanted them. We were choosing model 0, that's no interpolation, sky algorithm model F, where it looks over the entire field of view, and then finally 0 point for the magnitude scale is 22.5. I'm going to hit apply, although it's already applied. Oh yes, we do need to apply it because it's going to recompute the sky background. Because it's a new image, it does have to do that. So we hit apply and we say yes. Those options are just fine. I hit compute and it's done. And now we close the window. On the big button on the right here in the middle, It means 10, 10, 0. 10 is the major radius. The second 10 is the minor radius. The rotation angle, if it were an ellipse, is 0. But this is where we wanted it. It's circular with a radius of 10. So I'll hit apply and close, and that's fine. I hit close. And now we hit recompute photometry because we need to apply that sky background. So I hit recompute, and it brings the color table up, which I don't need. Okay. Now let's see where we are in the notes. So we've been 92, 93, we just hit recompute. Now we have to check to see if we had completely erased the old results. So go back down to the bottom left. The bottom row has save results, list results. Click on list results. Good. There's no photometry file. So that's okay. Now we're going to go to the source list, also on the bottom row, bottom middle right here. Okay. In this case, we already have a source list. So if you're looking at the instructions on page 94, it says here, if you already have a list of sources, say from an image in a different filter, which we do, then you skip these parts and you go on to this one. So we already have a list of sources for the cluster, so we click Choose Source List. Choose Source List. Okay. So our list of sources that we had was, hang on here, file the image name, target name, NGC 5466, G filter, sources xy.txt. So open that one up. And once again, I've got to make the window wider so I can see everything. Now, the next part here is very important. When I was testing this out earlier, I made a mistake and I left it as pixel. Actually, hang on. Now I remember I did have to make a new list of sources here. So that's one thing that I forgot to do to tell you. We have to get the equatorial coordinates out of our targets here. So we're going to need to make that. Now let me find where I put that in the instructions. Okay, that's page 94. We'll come back to that. Okay, page 96. So I had us go back just a little bit too soon. We have one more thing we need to do. Because our red and green filter images are not perfectly aligned, if you had it off by 1 or 2 pixels, that wouldn't be a problem. You see, the radius of the aperture is 10 pixels. As long as the centroid of the star, that is the weighted average for the center of the star, is shifted by less than the radius of the aperture, then it should be able to shift the aperture over automatically and find the new center. However, our shift is more than that, or it's on the edge, but it is, I believe, more than that. And so what we need to do is we need to make a list of the sources using equatorial coordinates. Okay. So we're going to do that right now. There are a couple of ways you can do it. If you have a sophisticated text editor like Emacs or maybe VI, you can open it up and you can copy the columns that have the right ascension and declination. Or you can, if you have a spreadsheet, which is what I'm going to do because it's a little faster, in fact, quite a bit faster, you can simply copy and paste into a text file. Okay, so I'm pulling up a spreadsheet. Excel, Google Docs, you should be able to do the same if you don't have one installed on your computer. Okay. Now, what we do is, let's see, I need to go to go to this here. Okay, so NGC 5466 G sources XY. Oh, nope, sorry. The photometry. We have our G photometry there. Now, if I open this up, I'm going to open it up as let me show you in the text editor first of all. This is what a comma separated value file looks like in text. Okay, so it's a bit of a mess. Each row is a row, but then each column is separated by a comma here. And so the end of the row, see, all of this is the first row. Whew. So it's not easy to copy and paste columns, but there are ways you could write something in Python that would be able to parse this and do it very quickly. But it would take you a little bit of time to write the program. No, maybe not too long. But if you open this up within a spreadsheet, it will put it into columns automatically. So here we go. I'm going to make sure all readable documents. Oh, I have to import it. Yeah. And I can double click on the CSV file and it will automatically come up here. There we go. So our second and third columns have the right ascension and declination. You could do the centroid, but I don't think it really makes that much difference. Okay, right ascension, declination. I'm going to copy these and I'm going to go into a text editor. I've got a blank file and I paste them. That is the easiest way to do it. And you can leave the headings on here, the column headings, Aperture RA, Aperture Dec. Okay, so save this as, let me see here. Here we go. Our target name, NGC 5466. The filter name, G. Sources, because this is the list of sources, not the photometry. And EQU for equatorial. So right ascension, declination, not XY. You see down here, we've got XY. I'd labeled it old. Here's the XY.text and then .text. Okay, I'm going to hit cancel because I've already saved it. You should hit save. Okay, I'll get rid of that. And then we can just close that. I don't want to save the stuff in the clipboard. Okay. And I'll quit Excel. So now we have you should have a 2-column file with a tab or spaces in between the columns, not commas. Okay. I will say that there is a lot more setup to do this kind of work than there was for the exoplanets last week. But once we got these done, then we get to go on with the fun part with the analysis, which will be next week. Okay, so let's see here. Let's find where we are. Equatorial coordinate list. Okay, that's what we've got. And now we run APT on the R image. Okay, sure enough. That goes back to page 94. So select source list. We already have it. So we choose the source list. And we need this thing in equatorial coordinates. So choose source list. Okay, this is why we label it carefully. Sources-EQU. I've chosen it. But don't make the mistake of leaving it here with pixel, because it will assume that the right ascension and declination are actually pixel coordinates. I did that back earlier tonight when I was reviewing this, and it was not able to find anything. So we click on equatorial. Okay. By the way, it may also be useful. Check the box to overlay the sources on the image. In case it's going to draw green circles on the image in order to show you where they are. And in case it has a problem, you'll be able to see it. All right. Automatically process the source list. And here you can see, and sure enough, it is circling the stars. It's very close to that there. There's not much of a shift, so that's okay. It's able to find them. And again, on my computer, it will take it about 1 minute. On yours, it may be faster. If it's slower, you're actually rather lucky. You might be able to go and make a cup of coffee in the meantime. Tea, I guess it would be more appropriate, right? Okay, I'll use this chance to see what we're going to do next. We do confirm that it has 2,388 sources, so that's good. It found that. Okay, process source list. That's what we're working on now. I will note something else here. In older versions of the Aperture Photometry tool, it would sometimes hang at 40% or something like that in processing the second filter's list of sources. And the reason was there was some kind of a memory problem. And so what you had to do was to, see, I've got a footnote here. Here we go on page 97. I think it was using up too much memory when processing the second filter. If this does happen to you, quit the program after you do the first filter and then restart the program before you run the second filter. But I haven't seen this problem in several years, so the new versions, I think they've fixed it. Mine is still a little bit slow, nevertheless. Okay, almost finished. I'll also say that back 5 years ago, 7 years ago, when teaching this the first or second time, some students, it would take it an hour or several hours to run this here. Maybe they would leave it overnight. Luckily, that is no longer the case with our faster computers today. Okay, it's gotten it. Done with the source list. I'll close the window. Again, now it's gotten rid of those green circles. All right. Now we're going to do the same thing we did before. We will list the results. Let's confirm that it has 2,388 targets. That's the case. We will export the contents. Once again, we reset the comma separated value file name. All right, now we have the target name, R for the red filter, and phot for photometry, so that we don't confuse it with the source list. And we've got to have .csv at the end. Okay, choose that. And I don't want to override it, but okay. Don't select any of these options here, and then create CSV file. Since I've already got it, I'm not going to do that. I'll simply close. Let's make sure that that file exists and that it has the information we want. And sure enough, there that is. Okay, So we are good to clear the contents now. Yes, we want to clear it. Okay, that has got our green and red filter lists. In principle, we're ready to start on plotting the color magnitude diagram. I'm going to pick that up next week though, but I've got a little bit more to show you tonight because the Sloan Digital Sky Survey is not the only place you can get these. And for some, it's a ground-based observatory. It's a 2.5 meter telescope. It's not bad. It's not very huge, but we can get in many cases, a better, well, we can certainly get better resolution if we go to space. Let's take a look at how we could do that. So I'm going to quit APT. All right. And I'm going to bring in my web browser. Okay. Now, let's see here. In order to get images from the Hubble Space Telescope, we're going to go to the same archive that we did last week for the exoplanets. So type in archive.stsci.edu. I'll post that in the chat window. While I'm doing that here, while everybody else is getting caught up, we've got a question from Ovid or Ovid. He says, I'm trying to create the source list and the program is stuck at 75% following the same steps. I tried to restart it, open the file again, but it's stuck again at that point using an i5 with 8 cores. Okay. If you quit and open the file again, let's see. You're creating the list in the first place though, or are you creating the list in the first place or are you processing the source list? Which step is it? Let's see, while I wait for him to reply, we've gone to archive here and whoops, I think I already clicked on it here. Did I? Well, that's what I wanted anyway. Access masked data.
Hello.
Yes, go ahead.
Yeah. I'm trying to create the list.
Mm-hmm.
It is a new list, and as you have followed the steps, I am following the same steps.
Okay.
And it is not happening. So it is stuck around 75%. What I tried is again to switch off the whole program, start again. Even tried to use the memory in graphics card, but
Uh-huh.
still done. So I think, but I have left all the defaults as default. So
Okay. I'll have to think about that. It's the first time I've had that happen in a few years. Let me see if that's, I think that's on a different, that your problem is at a different step than I was used to seeing the problems. Let me check here. Okay. So yes, usually it was during the list processing when it would hang up rather than the list creation.
so I will try to share a
Okay, if you're able to do that.
screenshot if I can.
And I'll bring up the APT website. Because they do have the frequently asked questions. Let's see here. Aha, look at this. They have precisely your question answered here. If you go to, and I'll pull this up so you can get it directly. If you go to this here,
Yeah.
all right, I'm going to select that. 75%. When running it on a large image, the source list creation may hang at 75%, probably because it ran out of memory. So here are some steps you can go through to increase the memory allocation. And there is an option to change that too. So it may be because of the image size on that.
I think it is more of I'm using Windows computer. Even in
Oh,
TopCat,
okay.
I had the same
Yes.
problem. I had to allocate memory. So
Okay.
probably that.
But try this when you get a chance then
Yeah,
on
sure.
it here.
Sure.
I'm very glad that you mentioned that because I had not known that that was a problem at this step until you mentioned it.
I will try it and let you know.
Okay. All right. So now let's go to the Mikulski Archive for Space Telescopes, MAST. So we go to Access MAST Data. And this is I'm going to say our new portal. It's actually a few years old at this point. I was on the archive users group, pardon me, for a few years, and they would get to show us all the new stuff that was coming through. So I've had a little experience on it now. It used to be that when you went to get data from the Hubble archives, that you had to create an account, and then you had these specialized software tools to do it. And it was a little clunky to go through. They are trying to make it to be where it's more like shopping on Amazon, where you have a shopping cart and you can put files in the shopping cart that then you go and when you check out, you download them then. All right. So there are several sub windows within this screen here. And that's the main window there. There's a bit of tutorials available as well. User's manual and help. This is the top center. Okay. If you can use it anonymously or you can log in. And I do have an account, but we don't need it for this right now. But if you're going to be doing a bit of this and if you want to look around on it, yeah, I'd recommend making an account then. Okay. So search a collection, we don't need that right now. We can just put the target. We can leave it on the default collection. And our target is NGC 5466. Oh, you know what? I'm not even sure if it's looked at that one. Well, you know what? Let's find out. Try this. And hit search, enter. Hey, there we go. It has looked at it. Well, remember that it's not only the Hubble Space Telescope that we use here. It's several different telescopes, space telescopes that they have the data from. The TESS, this exoplanet search telescope, has looked at it. SWIFT, which is an X-ray telescope. X-ray, gamma rays, visible and ultraviolet as well. Hubble Space Telescope is HST. So under mission, it's everything in astronomy is an acronym these days, but it's good. It's good to learn them very quickly. Okay, HLA is high. Let's see, Hubble Legacy Archive, which is other Hubble images. GALEX was an ultraviolet telescope, and that's what that is there. All right. Let's go through one which I know is a better source, or is a good source anyway. And that is M75. Okay. This is one I've tried out. So let's go to the target field and enter M75. And I'll show you what the features are around here. Again, because this is a workshop on archival data, I hope you'll make good use of the MAST archive. Okay, now, again, it can be a little intimidating at first, but on let's see here, it tells you how many different entries it has for this. This is separate observations usually. Here it tells you what the target name is. And what it did was, see, radius, basically, it took the name and it went to a service to identify that target. and turn that into right ascension declination coordinates. There are two popular ones that are used, and you may already be familiar with them. One of them is NED, that's the NASA Extragalactic Database. I'm going to put that in the chat window. So if we put in here M75 into NED, it comes back with a lot of information about it. Now, this does not store files. Well, it stores a few, but not really many. Mostly, the NASA Extragalactic Database tells you about what people have found about this. And one of those is the coordinates. So here are the coordinates for this target in equatorial coordinates. If you may be familiar with the epoch, this is a coordinate system based on where right ascension and declination were in the year 1950, and J2000 is based on where those coordinates pointed in the year 2000, because there's the precession of the Earth's axis. And they turn it into longitude and latitude. In the case of right ascension declination, longitude is right ascension, latitude is declination. Decimal degrees, sexagesimal, hours, minutes, and seconds, or degrees, minutes, and seconds. And then if you go down to galactic coordinates, you have galactic longitude and latitude, and then we have other forms as well as ecliptic coordinates, which we don't tend to use as much. Okay, so that's useful information. And also, if you need to look up papers that have been written about it that mention this, it will not get every one of the papers, but it's a good quick first look in reverse order here. Okay. Oh, they've got it all the way back to 1888 with the original New General Catalog. Okay, so this is, if you want to find the coordinates, go to NED. So MAST enters that there, and it searches within, by default, 2/10 of a degree in a circle around that, and everything within that it assumes is an observation of that target. And you can select tighter searches or wider searches manually. Okay, let's see here. On the far right, we have a picture from the probably the digitized sky survey that I mentioned before. And so there's a picture of the sky in this region. And then these rectangles, these are the footprints of individual images, where those would fit on the sky. And so you can see, see these little pictures here, these are close in ones. That one that looks like the bat wing from the Batman, first Batman movie, that is from the Hubble Space Telescope's Wide Field Planetary Camera 2. And then these rectangular ones will be some other cameras. These wide ones are maybe from other missions. And the big circular one here, that's going to be from Galax probably, that ultraviolet telescope. And it made circular images. You can zoom in and out as well. Okay. Clearly that cluster has been a target, an intentional target by a lot of these. Okay, so we can even select individual images that way, but let's do it more carefully. On the left side, it lists filters that we can apply. So which mission? How are they processed? Which camera? Which project? The filters that were used, I'll explain those in a moment. There are certain ones we want to use and others we might want to avoid. Waveband and target name. In this case, someone may have been looking on that, but they were not intending to get that target. They were intending to get something else. But this happens to be in the field of view. Classification. And so this is if you've got a lot of things coming up, you could shorten the list. In the middle here, we have every individual file, spectrum, image, calibration data, whatever. Okay, now we're interested in the Hubble. So I'm going to go to Hubble Space Telescope, HST. You might also select HLA, Hubble Legacy Archive. but I want to deal with the original images right now. Okay, which cameras do we have here? The Wide Field Planetary Camera 2 is the old original camera on the Hubble. I want to go for a later camera, and it has more rows it didn't display. Let's go for the new main camera. Well, new, it's several years old now. The Wide Field Camera 3. In this case, it has two settings: infrared, would be IR, and the ultraviolet and visible, UVIS, there. Okay, that's what we're going to come up with. If we scroll on down, we see that we've got filters. There are a lot of different filters available. Okay, well, there might be. So in this case, we want it with two images. You can see they're both aligned the same way here. They're overlapping exactly. Let's see this here. If we scroll off to the right, we see Hubble Space Telescope. Provenance, that's calibrated wide field camera 3. I think that puts it in a certain pointing there. Wide field camera 3, ultraviolet visible. Here we get the filters. Now, the filter names on the Hubble follow a regular pattern. F stands for filter. Then you have the wavelength of that filter. In this case, it's like the peak or the central wavelength, roughly. For the ultraviolet and visible camera, ultraviolet and visible settings, that is the wavelength in nanometers. So 438 is going to be blue. Yeah, blue. And then W stands for wide. That is a wide band filter, like your standard Johnson filter set. I was trying to think of the names of the Johnson filters. UV, let's see, UVI. It's a little bit late in the night here, and I'm not remembering them very clearly. Anyway, 555. That's going to be green. Yeah, green color there, 555 nanometers. Okay, so those are the two that we want. And then we've got coordinates. The time it was taken, the year 2010, May the 1st. The exposure length in seconds. That tells you something. If you've got a very short exposure length, it may not be worth your while doing it. 300 seconds for that one there. Long one and a short one. And that could be because the shorter wavelengths, it may not be as bright in that, so they had to go to a longer exposure. Okay, and this is the distance from the center of the search. So you can click this to select both of them, or you can select them individually. If you go up here, now take a look at these. Copy the link for the search. So if you want to come back and do the search again, okay, you get a link to do that there. And that would pop back up with all of what you had just done. Cross-match this table with other catalogs. So you could go to, I haven't used that in a while, so I won't try. You can plot things, data about the images, do math on it, position columns. Let me skip over. Export the data in the table to a file. All right, but what we want is add these to your download basket. That's your shopping basket there. Now, if you wanted to go get some others, you could keep on doing that, like continue shopping and then check out in the end at Amazon. Right as it is right now, we're going to download these now. So in our basket, we have this one set here of Hubble Space Telescope. If I click on the arrow, it shows me the two data sets. Depending on the camera you're using, you may get different data sets, but the first one says ASN. So the code here tells you, if you know it, about a little bit about which camera and so on. But ASN is association. It's going to associate things from this file to the final one. DRC, I don't remember what that is, but the one you actually want to analyze is DRZ. That stands for drizzled. And what they did is they pointed in several different directions, slightly shifted from each other, and then they did a technique called drizzling to combine those different pointings into a single image. And this is used to, there's what's called a dither pattern. where you do slightly different directions that you point in, but a lot of overlap. And when there are bad pixels, you're able to eliminate those. And by doing several different pointings, you can also get rid of cosmic rays because you split them up. You split up the total light between several different exposures. Okay, but it's the drizzled one that you're going to analyze there. Remember, when you download this, you just click on download here. Zip is going to combine them, and you will certainly want them combined because they are big files. Then you click on download. Make sure you've got about a gigabyte of space available. I've already done that, so I don't need it right now. Oh, except, you know what? I deleted it because it was so big. So let me do this so I can show you what one of those images looks like. And we'll finish up. Okay, download. Oh, I don't need to do that. Now, why is it waiting on me? Because it goes here. Okay, show in Finder. Removed. Well, of course, that's because I did remove it, didn't I? All right, let me try this again. There we go. Okay. So I had a little glitch there. It looks like it's reloading the page. I'm going to go to my external disk. I'll save it here. Okay. And now we can close this. And looks like it's still downloading, so it may take it just a minute here. Now, the WFC3, that stands for Wide Field Camera 3, WFC3, is the current main, it's pretty much the main camera on the Hubble. It covers ultraviolet, visible, and infrared wave bands. And I'm going to show you if this will come down in an appropriate amount of time. It may just be that it's such a large file. It's going to take long. When I got my internet went out and I had to switch internets, it may be that I'm going on something that's too slow then. So we were looking at, let's take a look at the name of that thing. Let's see, the basket said, okay. I think I've got that actual file here. All right. So IBM, I think that's it. All right. Let's take a look here. Open it up in DS9. Now, scale, let's go to logarithmic, minimum, maximum. Actually, let's go to Z scale. That always gets us a good quick look. Scroll out. I'll pull up the parameters so I know what the bright and the low limit should be. Let's make the bright limit be 100. That's pretty good. All right. And this is our cluster here. Now, the first thing that we saw was that there's a gap running across the middle of the picture. This is because the ultraviolet and visible settings are actually have two separate camera chips that tie together, but there's a little gap in between where the electronics runs. And you just have to live with that gap being in there. Let's see, Vandana asks, what is calibration level 3? Let's see, where are we finding that here? Could you, oops, and it is not enjoying me clicking on that there. I think it's downloaded now. Calibration level 3 is, it's a step in the processing. I think that that is the most complete, I think that's the most complete level of processing. Could you tell me, where are you seeing that? It's on the masked page somewhere here. Just unmute your microphone and you can ask.
Yeah, this don't have file to download. So where we have all the data, the filters, the wave band.
Yes. Okay, on the left-hand side here.
Just after right ascension and declination, I have.
I see calibration level here.
Yes.
Yes. Let me think. It's been a while since I've had to deal with that. I believe that it is steps in what are called the pipeline processing. So when you get, to tell you the truth, I was kind of spoiled. I started with the Hubble as a graduate student. And so I got to use really what's just about the best telescope in the world right from the beginning. And I have not usually had to do that much calibration of my own images then because of that, because they do it for you. I found out when you go to other observatories, you have to do a lot of this stuff yourself. Well, the images that come straight from the telescope, um, the raw images, have to go through several steps of calibration. You have to calibrate the brightness levels and so on. And they also have what's called geometric distortion. So if you are, let's see here. Okay. I remember now. So you're going from first to second level. I think it's accounting for the geometric distortion. If the camera is not on the axis of the telescope, then it has to do that. Going to level 3, I believe, is where they combine separate camera exposures into a single drizzled image. That's the DRZ file that I mentioned that you'll actually use. And I might be saying it wrong, but I think that that's what calibration level 3 is. Anyway, that's the one that you want to use for your scientific work then. Does that answer it well?
Yes. So is this the highest level of processing of the raw data?
Yes, it is the one that you can use for photometry. Earlier state, I guess there are ways of using earlier stages in photometry, but you'd have to account for more things that have not been calibrated yet. So calibration level 3, it's ready to use science data.
Okay, thank you.
You're welcome. Okay, so here's the center. Now notice, by the way, this is a good point here. Notice that the cluster is not centered in the picture. It's off to the side. And the reason probably is for this one that they were wanting to avoid putting the center of the cluster with all those stars in this gap here between the two chips. It's great to have the extra space by the extra chip, but it also means that if you center something perfectly in it, you'll be losing data right in the middle where it might be the brightest. So they tend to center it in one chip or the other. Okay, so let's see which filter we have. If you go to File, Display Header, now you've got different options here. This is a FITS file which has different extensions. Basically, it's several separate files stuck together into one. You have your, well, at least you have two headers in this case. This header will tell you about maybe the general camera settings, and then the one that has the science extension, SCI, pardon me, SCI, that will tell you other pieces of information. And you never really know until you click on it which is going to tell you which. Okay, I clicked on science, and I'm kind of thinking that's where the filter name will be here. B unit, brightness unit, is different for the Hubble than it is for the Sloan. In the Sloan, they used nano Maggies, and that's again because they use this what are called acinch asymptotic. Let me think. Asymptotic hyperbolic sine functions for their magnitude system. So if they go down to negative sky fluxes because of little variations, they don't wind up getting a failure in the when they take the logarithm to get the magnitude. Um, anyway, the Hubble is using electrons per second. And the reason you get that, it's not photons per second, but each photon that hits the detector, a pixel in the detector, liberates an electron or several electrons between a high and low voltage anode, an anode and a cathode. And so it spills those electrons out and it creates a current, and that's amplified. So the detector counts the number of electrons, and that each electron, one photon corresponds to several electrons, and that depends on what's called the gain setting, the amplifier gain. Uh, you just need to worry about how many electrons per second, and then what is the magnitude 0 point for the flux. So you have flux in electrons per second, and your magnitude 0 point will allow you to convert that into magnitudes. For this, actually, that's something I should show you. How do you find the magnitudes? I also want to define the filter, and we have to know the filter before we know the magnitudes. Here we go. Photometry mode. Wide field camera 3, ultraviolet visible. Let's see, I guess that's 2 would be for chip 2. And here's the filter, f438 wide. So that's filter with a the blue filter, basically. Okay. So if I put these here, I'm going to copy that. I'm simply going to go to the web. Now we've finished with the archive. Okay. So HST, I'm just going to paste this into Google. All right. So we can pull up the instrument handbook for the wide field camera 3. And let's actually UViz, let's put 0 points. Sometimes that's just the fastest way to do it, is put the whole phrase in Google. Here we go. Wide field camera 3, UViz photometric 0 points. 2 ways to get to it here. And I'm going to copy that and put it in the table. All right. Now, a thing is, you have different photometric standards you can use, magnitude systems in a sense. Depends on what you want to calibrate it to. There is the traditional Vega magnitudes, which are based on the star Vega having a magnitude of 0 in every filter. There is more recently, there's been more of a push to use kind of standardized systems of magnitudes that don't depend on a natural source. And one of them is the AB magnitude, and another is ST magnitudes. ST, I believe, actually stands for Space Telescope. And AB, I forget what that stands for. But in one of them, the source, an artificial source, would have the same brightness per unit wavelength. And in another one, it would have the same brightness per unit frequency. And you just have to look up which is which. So you need to specify which magnitude system you want to use, either one of those or Vega magnitudes. And we should be able to scroll here. Instrumentation, photometric. Hang on. That's not as good as what I was wanting. It could be my browser, but I'm only seeing the first few filters in the ultraviolet. So anyway, you might have to look that up here. Let's take F438 wide and see if we can come straight to a page there. Okay. So if you get to the data handbook or the instrument handbook, it should also have that. But I have found a page that has all of them just in a table. All right, you might have to look around a bit. But anyway, oh, another thing to look out for. You will, with star clusters, you're unlikely to see this problem with the Sloan Digital Sky Survey. But if you search around in the Hubble, and there are a lot of globular clusters that are in the Hubble archives, you will find several stars that are saturated. Okay, let's take a look at this one here. So, have you come across this before? The diffraction pattern, let me show you what the diffraction pattern should look like for a star. Well, okay, it's everything that you see here except for the vertical line. Now, the edge of the aperture will make a diffraction spike, a streak that's perpendicular to that edge and with a wave pattern on it. If you have a strut that holds the secondary mirror in place, it'll make a streak perpendicular to the strut. So the X-shaped struts holding up the Hubble's secondary mirror. Priya says, wasn't the 0 point in the header negative 21.5? It is, but I always forget that's only for one of the 0 point, only one of the magnitude systems. And I've forgotten which it is. Hold on, let's display it again, because that's a good point here. Display header. Let's try to the science image here first. Okay, so here's one. This is the ST magnitude 0 point. It's negative 21.1. So if you're using that system, then you do have it in that. Okay, thanks. Priya had found that for us there. And Ovik says the source list is created and processed. All right, so someone was able to find that. Ovik was able to find the how to free up the memory when doing the making the source list. Okay, so we do have the ST magnitudes here. If you want to find it in another system, then there are transformations or there is a table to look it up. And but luckily that one system is there, and you could just use ST magnitudes. Let's also see what's in the other header. If I do the main header, this gives me the camera, the target, right ascension declination, who did it, Eva Noyola, the principal investigator, the date of the observation, exposure time 1,500 seconds. Okay, and a few other things like that. And we also have the a simpler version of the filter name right there. Okay, so yes, you can start with that ST magnitude 0 point. Thank you, Priya. Now, so the diffraction pattern for the Hubble Space Telescope is distinctively like this for the WIF-C3 camera and with the old Wide Field Planetary Camera 2, WIF-PIC 2, we pronounce it. You have diagonal spikes, and you have this kind of a ring bullseye shape here. This is called the Airy disk, named for, I think it was George Airy, the mathematician who had modeled this pattern. And we have the rings, the Airy rings around that there. So the problem here is that this very narrow feature is not from photometry. This is an error. And what's happened is that that star is too bright, or for an exposure time of 1,500 seconds. A CCD camera can only absorb so much light before it's filled at that pixel. One pixel can only absorb so much light or so many electrons before it's saturated. When that happens, you no longer have the information about how bright it is. It is truncated at that point. Furthermore, it can get worse. If you keep exposing past that point, the saturation, the extra electrons can spill into neighboring rows along the same column. And that's what's happened here. Now, when you do photometry, then you've got these leaked electrons here that will throw the photometry off. Now, to be truthful, they belong in the middle here, so they still belong to that star, but it's not calibrated well. You really should just mask this out, and you might interpolate into a model. But what we're going to check is that other stars are not saturated. And just looking around, I see that one has a little bit of saturation. If you have your brightness turned way down like that, you can see the saturation. And the value of that pixel will depend on what the units are. In this case, it's in the 100s, 140, something like that. It varies a little bit as they've flattened the field. Okay, so if you go to that brightest level, then you can see the saturation. As long as not too many stars are saturated, then you've got a good target you can work from, and otherwise you need to mask it. Okay, and I have found several of the targets in the Hubble that the Hubble's taken pictures of here um, that have saturation in them. Yeah. Messier 28, it's there, but it's saturated. This one here, M5, is also saturated, and I haven't checked out all of the others there. Noyola and hers, I think in general, those have been pretty good. Okay. So I think that is it for my presentation for tonight then. Next week, we'll pick back up here. If you have processed a few of these, at least 2 filters for each target that you want to do. And to tell you the truth, the filters I recommend, if you use the Sloan, use the green and the red filters. You can use others, but the green and the red will discriminate between different stellar types better. If you're using the Hubble, well, you just got to you take your pick of whatever somebody else has already picked for that. But it is useful if you have if you know about the horizontal branch stars. If you're looking in the V filter, the visual filter, which on the Hubble is between f555 or f606 wide, you'll get the horizontal branch being horizontal in either of those filters there. We don't really need that. We're going to do a more sophisticated method for analyzing it, but that makes it look kind of nice. All right, questions then?
Yeah. Questions? Maybe as a homework, they could try running AppFort for the HST image. But will that take too long because the image is so large?
For the Hubble image, did you
Yeah.
say?
Mhm.
That actually can be a problem. So let me see here. The WIFC3 image that goes up to, it's more than 4,000 pixels on a side.
Okay.
And I think, let's see here, I've closed out the APT. There is a maximum image size that can be displayed in the APT. So you've got 2 options. It might not be able to catch things that are beyond 4,000 pixels on the side. I kind of think that that was the limit. But the other, and you could just deal with that. You could simply
Yeah, they can just
do
cut it.
most of it. The other option is you could crop the image.
Mhm.
You could do a section of it. And so if they know some of the basic image tools with IRAP or something like that, then that would be an option too.
Yeah, actually, we've not done that as yet. We've taught
Okay.
them AstroPi, so maybe they can use AstroPi
Ah,
to cut it.
yes.
So because
Yes, I mean, that'd be a
yeah,
straightforward
what we did
Python.
is we didn't touch IRAF because I thought IRAF is an outgoing thing. So I think that the younger
Yeah,
generation, we worked with IRAF, right? I'm an
yeah.
IRAF user, but
Okay, let
probably
me.
the younger generation has to go with Astrophi.
We use
I would also encourage the younger generation, those who have good computer skills, please, 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 somebody create a complete set of tools in Python that imitate what was done in IRAF. There are still several useful IRAF packages that nobody has created a replacement for.
That's
And
true.
it's kind
Yeah,
of frustrating. Some of my students, they can't get the new IRAF in, but they also don't have the replacement tools for them yet.
yeah, that's true. That's true.
Yeah.
But yeah, so
Um,
we kind of didn't go into IRAF. We went into Astrophi,
uh-huh.
and maybe they can use that to crop the image, and then
Yeah.
yeah, but then they can run even DAO4 or App4 from IRAF itself. You know,
Yes. Right.
through that.
maybe we'll have a session on IRAF, just
Yeah,
give an introduction to them, because historically it has played a big role in analysis of astronomical data.
yeah,
Mm-hmm.
So we have some
right.
session to,
For some completeness
yeah.
kind of thing. Yeah.
Yeah, yeah. You'll still come across plenty of us older timers using it then, so
Yeah,
and
I
you may have
myself
it on
use
your
that.
computer schools. Yeah.
Yeah, that's right. Oh, yeah, you have a question.
Oh, okay, John Mora. All right. If I'm doing photometry on a star, he asks, and then when I zoom in, I see it's a binary star. Does this mean my photometry is poorly achieved? And do I have to do it individually to the two stars? Um, well, yes and no. I guess if you did it for the combined stars, then you would simply get a single brightness for the two together. And to tell you the truth, there may be many of the stars in this cluster right here, which are binaries. And if there are very close binaries, we simply would not know. Um, if you have a binary star and you're trying to do what we're going to do next week, which is the color magnitude diagram or the Hertzsprung-Russell diagram. Color magnitude diagram is just a version of the Hertzsprung-Russell diagram. It's going to classify the stars based on two things. Originally, it would have been temperature and luminosity. In the color magnitude diagram, we use color as a proxy, as a way of measuring the temperature indirectly. And if you have a binary star, if they are of two different temperatures, or two different types and two different luminosities, then yes, that will be a bad data point. However, if they are far enough apart that you can see them individually, hopefully the APT program, or if you're using Photo or one of these others that are out there, I guess there are Python versions of those now, uh, hopefully it would be able to separate the two. If they are very close binaries, or if they're in a globular cluster, I'm not sure if you'd be able to see separately the individual stars in the globular cluster if they're binaries. In that case, well, we got 2,388 stars. If we had 1% of those being, well, let's see here. Actually, I guess more than 1% are likely to be binaries, aren't they? In that case, I think we probably are doing a large number of those are being separated very well because we rarely have very many bad data points when we plot this. I don't think we really get it is something that people should correct if they can. And I think in practice with these globular clusters, you'll probably find that some of the data points that just they lie in a weird place.
Yeah.
I never thought about that before. Those may indeed be binaries in some cases.
Yeah, so may
You
I
have some experience,
interrupt?
Bree?
So typically in open clusters, you'll actually see a binary sequence, with the HR where you have the main sequence, you
Oh,
see it offset vertically where you have a binary sequence, showing, which is clearly
okay.
an indicator of the binaries of the cluster. So
Really? Okay.
yeah, so you'll actually get two parallel lines. One would
Hmm.
be the main sequence, and the other one is shifted upwards because it just got brighter but did not get resolved as two stars. So it's a
I
it's a
see.
brighter star, brighter than than a main sequence star should be for that temperature. So you'll get a parallel main sequence to the main sequence, which is the binary sequence, which is
And so
visible in a lot of clusters. You can do.
your uncertainties and magnitudes will have to be small enough. If you can see those two lines, that tells shows that you have the uncertainties small enough that you're able to resolve them. Then, right? That
Yeah,
you're
so
able
with
to
Hubble data, you
see
do
those
get
areas,
that.
right?
With
Yeah.
Hubble data,
Okay.
you do
Okay.
have color magnitudes of that kind.
Uh huh.
Yeah. There's
Okay. A
another
second
question.
question
Yeah.
here is from um, I'm
last
sorry.
Friday.
Let me try pronouncing though. Mru, Mrunalini,
Yes,
Mrunalini,
Mrinalini. Mrinalini.
Mrunalini, Mrunalini.
Yeah.
Okay. From the last class on the light curves, some papers plotted the square root of n as the error value for the flux. Can we use the same for Kepler 6b? So square root of n is the error value of the flux. So in this case, can you tell me, was n the number of individual transits or the number of individual observations, perhaps? Which one was that meaning?
That n is number of data we got. Is that correct? I don't know what is that n. The n is the number of values. That's what I
Data
used.
points. Is it the data
N
point?
number of data we got. Is that right?
Let's see, there's a little computer sounding glitches on my end there, but let me see if I interpret it right. Uh, the number of values that were there. The When you're doing counting statistics, those are Poisson statistics, and so the square root of the number will be the uncertainty then, and so that would be error value in the flux. It's the error value in the number anyway, but I'm not sure if how that applies to the flux. If you have a paper reference that you can send me, I'll take a look at that over this week, and I'll see if I can answer that for you.
Mhm.
Thanks.
Yeah. So, any more questions? I think, yeah, I think we need to let you go to sleep now.
That's what my wife would say too.
Because I'm all the time worried that, we're keeping you up so late. And so I think they can use the week to pose their questions next week. And,
Okay, all right, good.
so thanks
Well,
a lot,
I'm
Tim.
glad that they've been digging into those as well. That's been great.
Yeah, no, we do have some good enthusiastic students. We're just keeping up.
Yes, yes.
Yeah.
All right. Well, thanks again, everybody. I appreciate being invited into this, and I will see you all next week then.
Yeah. See you.
Thank you.
See you, everyone. Bye
Thanks
bye.
a lot.
Thanks a lot,
You're
Tim. Bye
welcome.
bye.
All right. Good night.